How a Japanese house survives an earthquake with no nails. The building is called a minka. It translates to the people's house. Built mostly during the Edo period, these were the vernacular dwellings of Japan's farmers, fishermen, and merchants, distinct from the heavy fortifications of the samurai class. Today, structural engineers travel from around the world to study these centuries-old timber frames. They take them apart, place the joints in laboratories, and shake them. The fascination stems from a structural contradiction, a building made entirely of wood, paper, and grass that regularly endures some of the most violent seismic activity on Earth. Modern Western engineering often approaches an earthquake as a force to be resisted, demanding rigid walls and deep steel anchors. The minka relies on the opposite philosophy. It is engineered to yield. To survive, the structure absorbs the violent kinetic energy of the earth and translates it into a carefully controlled, flexible dance. We can break down this ancient mechanical response into 4 precise steps. Step 1 is the skeleton. The Japanese carpentry tradition that builds the minka is called Kigumi, or wood joining. Posts, beams, and braces are cut into complementary geometric shapes that slot directly into one another. The load-bearing frame requires no nails. The geometry of the joint itself is the connection. Consider the nuki. A beam passes cleanly through a square hole in the vertical post, secured by a small wooden wedge. In a still room, it appears entirely rigid. But when a tremor strikes, the beam rotates inside the post. As the wood turns against wood, the friction of those tight surfaces actively absorbs the energy of the shaking. When the ground finally stills, the joint naturally slips back toward its original 90-degree angle. By multiplying those small, controlled rotations across dozens of intersecting timbers throughout the house, the Edo carpenters created a highly effective mechanism for energy dissipation. Step 2 is where the house meets the earth. A traditional minka post is never buried or bolted into the ground. It rests flat on top of a rounded footing stone, known as an ishizue. The timber is scribed to match the rock surface, held in place by gravity alone. Pinning a column to the earth forces the timber to absorb the full force of the tremor. Leaving it unanchored provides a mechanical disconnect. During severe shaking, the entire timber frame can lift slightly, slide laterally across the stones, and reseat itself. Contemporary engineers achieve this exact same effect in modern skyscrapers, using complex rubber bearings and sliding steel plates that cost millions of dollars. Centuries ago, builders achieved this critical base isolation using an untreated log and a river stone. Step 3 sits at the very top of the house. A minka roof is incredibly heavy, whether piled with a meter of bundled thatch, called kayabuki, or laid with thick clay tiles, called kawara. Placing a massive weight at the top of a highly flexible, unanchored wooden frame seems like a structural error. In practice, the mass acts as a pendulum. The sheer inertia of that heavy roof actively fights the rapid shaking of the earth. It slows the sway of the wooden frame beneath it, forcing the building to vibrate at a lower, safer frequency. Gravity itself operates as the main stabilizer. It is the exact mechanical principle of tuned mass damping used today to calm the sway of super tall towers and high winds. Step 4 is the interior space. The heavy loads of the roof and frame are funneled through a very small, specific set of thick pillars, anchored by the primary post, the daikokubashira. Because the load path is isolated to these few timbers, the partition walls carry almost zero weight. Instead of plaster or drywall, the rooms are divided by light paper screens, opaque fusuma, and translucent shoji that slide on wooden tracks. Because there are no rigid shear walls, there is nothing brittle to crack. The rooms simply deform and breathe with the swaying skeleton. Because the frame is pinned with removable wooden wedges rather than permanently nailed, the minka is inherently modular. It is entirely biodegradable. When necessary, the whole structure can be unpegged, dismantled, transported, and re-erected on a new site. If you appreciate reading real buildings back to their underlying reasons, subscribe to How the World Builds. Most of us spend our lives in rooms designed to feel heavy and unyielding. The minka offers a deeply different philosophy, a structure designed to remain light, empty, and adaptable. The system is brilliant, but it is not invincible. During the 1995 Kobe earthquake, and more recently in the 2024 Noto Peninsula earthquake, traditional timber houses collapsed in large numbers. The failure mode is almost always the same. Over decades, unmaintained wooden joints loosen or suffer from rot, weakening the lower frame. Simultaneously, generations of patching and repairing the roof layer by layer add excess weight. A meticulously maintained Kigumi frame will dance with the shaking earth. A neglected frame, compromised by damp and carrying too much mass, will be crushed by its own damper. The survival of the minka relies on a perfectly balanced chain of mechanical reactions. The joint rotates, the footing slips, the massive roof slows the sway. The empty interior flexes without cracking. The Edo carpenters who perfected this architecture lacked the vocabulary of modern physics. They achieved this highly tuned system through direct observation, walking through towns after a massive tremor and studying exactly which joints and which foundations were still standing in the rubble. Contemporary structural engineering has spent the last 40 years catching up to that vernacular logic. We now use terms like energy dissipation and base isolation to describe what builders were already accomplishing centuries ago, with careful cuts in timber, smooth stones, and bundled grass. Every building is an answer. Tell us in the comments, what modern building near you is rigid where it should be flexible? Name it.